All right. Sorry, this is going to be a little bit late. I'm not going to get this up till Tuesday morning, but this is meant to replace the Maple Lab that we would normally have on Monday nights. We're going to be taking a look at the first two problems on the Maple Lab, and I'm going to be introducing something called Euler's method to you. And just generally go over some of the things to look forward to on this Maple Lab. The first thing is I have moved back the due date from what was originally in the schedule. It was originally meant to be due this Friday, but that's a little too quick after the first one was due. So this will be due Monday. So you'll have this coming weekend to work on it. And I just want to encourage you to ask questions about this, either through email or talk to one another, work on it together. One thing I need to say about working on these together, make sure that you're doing your own work, right? So don't just copy someone else's file or someone else's work. Even if you worked on it together, do your own work on your own file. Just make sure that it's yours, okay? So I know it's tempting to let one person do it all and then spread it out, but that's not appropriate. So I just want to make sure that we understand that and that we've talked about that together. This particular Maple Lab 2 that you're looking at has, I believe, 8 questions on it. We're going to do the first 2 together. The third one, question number 3, is based off of the parameters and bifurcations that we're looking at in class. We started on Monday. We're going to continue to look at it in class on Wednesday. You're doing some more parameters and bifurcations on 4 and 5. And 6 is just an autonomous slope field. You're just going to plot some slope fields and talk about what you see there in regards to equilibrium solutions. So there's really not much to problem number 6. And then problems number 7 and 8 deal with existence and uniqueness of solutions, which is something we're going to talk about Friday in class. So you should have all the material by the end of this week to be able to work on this lab. We're going to start with the first 2 questions together. Question number 1 is simply an autonomous model. It's an autonomous model of learning. So it's trying to describe the rate at which someone learns new material. So I'm going to start by just go ahead and writing down the differential equation, talk through a couple of things here with you. The differential equation in this case, I'll just name it ODE is, or ODE1. The differential equation here is the derivative of L with respect to t is equal to k times 1 minus L of t. And one of the things I noticed on your Maple Lab 1s that you really need to be aware of, the dependent variable should always be written as a function wherever it exists. So even though in the Maple Lab it says 1 minus L here, this L is L of t. It is a function of t. I saw that a lot on the first Maple Lab, and I just want to make sure that we understand going forward that that's something you need to do on all the rest. So it says in part A here, analytically determine for what value does learning occur most rapidly. So this is something you don't even really need Maple to do. You can do this just by hand. You can simply say, so on part A here, you can simply say that learning occurs most rapidly when the derivative is largest, right? That's what it means. That's what most rapidly means, right? So if you look at the derivative is this piece over here. When is this the largest? Well, you can clearly see that k times 1 minus L is largest when L is 0. This means learning occurs quickest when you know nothing, which makes a lot of sense. The less you know, the quicker that you learn, because there's more material out there for you to learn. I think that would make a lot of sense in the context of this model. One thing I do want to mention about the model here is that, the parameter k here is positive. And L, if you read this, L corresponds to the fraction of the list learned. So our values of L will always be between 0 and 1 because it represents a proportion of the amount learned here. So if L was 0.5, it means you've learned 50% of the list that you were supposed to memorize. All right, so on part B, it says separate variables and find the general solution. So I would encourage you to separate variables and do this by hand just as a practice, but we're going to use dsolve here. So on part B, I'm going to go in and use dsolve to solve this ordinary differential equation with L of t, for L of t. And so you can see here that it's a decaying exponential of sorts. One thing I would recommend that you do or get in the habit of is assigning this to a function. One way to do that is maybe create a function. I'll just say list as a function of t. So it's like list memorization, if you will. That's what we'll call it. And I just want this piece right here. So I can copy and paste that piece down, or I could do what's called the right-hand side. So I could take the right-hand side of, and you see how this is labeled with equation 1.1? You can actually use that to reference this output. So the way that you do labels in Maple is you hit Command L if you're on a Mac or Control L if you're on a PC. And then it asks for the identifier, and the identifier is the label number. So I want the right-hand side of 1.1, and now that's saved to the list. The only problem with using this right now is it's in terms of a constant, right? So I don't have any specific values in mind here of what my initial condition is, but I could easily fix that. I could go back in and say, all right, let's look at if someone knew 20% of the list to start with. So if someone knew 20% of the list to start with, then now I have that equation saved. So that's now saved to this function that I've named, okay? So just some ways of handling things like B. It also asks what role does K play in the model? And you can see that for different values of K, it's going to, because K is the decaying term, it's going to speed up the rate at which you learn. So K is related to the speed of learning. I would encourage you to look at units. So if you're looking at the differential equation on the left-hand side, L refers to the percentage of the list memorized, and T is with respect to time. Now it doesn't tell you what the units for time are. Let's just say hours. So percentage of the list per hour would be the units on the left. 1 minus L is still percentage of the list. So K is actually inverse time. So K is like what percentage can you learn per hour, right? So it's like a rate of learning. So just something to think about on the value of K there. So here on part C, we've actually specified a value of K. So there's no need to write a different differential equation for this. I just need to update the value of K. So I'm going to go in and say K is now 2. And you notice if I type in ODE1, it's already updated it with K equal to 2 in there. So now I can actually solve this thing and get something that's usable for me. So the question asks on C, if one of the students knows half the list at time 0 and the other knows none of the list, which student is learning more rapidly? So if the student knows none of the list, then the solution there would be, well, let's just plot the two against each other. That's probably the better way to do it. So if I use my DE tools package, and I'm going to do DE plot, then I'm going to do a DE plot of ODE1. Go plot for the list. Let's see, my T range will be from 0 to, I mean, there's different T ranges that you could do here. If we're doing in hours, maybe like 2 hours or 3 hours. The list would be from 0 to 1 because remember it's a percentage. And then I'm just going to plot the two things that it mentions. It mentions someone who knows none of the list versus someone who knows half of the list, right? So that would be the two conditions that you would be plotting there. So this is the learning rates associated with someone who knows none of the list and then someone who knows half the list. Now, the question asks, who is learning more rapidly at this instant? Well, earlier we said that the highest speed of learning occurs when you have virtually none of the list memorized. So L of 0 equal to 0 here, you can clearly see that the derivative is sharper initially here, but it levels out over time. The other feature of this that I want you to pay attention to is this is an autonomous model, right? The independent variable t does not show up on the right-hand side of the equation. So because of that, you can see along every horizontal line in the slope field that all of the slopes are equal. What this means is that any two solutions to this model are simply horizontal translates of one another, meaning if you have one solution, like the solution that starts here at 0.5, the solution that starts here at 0 is simply has the exact same shape. So there's simply exact same shape, just shifted over, in this case, by a certain amount. So this point here matches this point here, and the curves are otherwise identical. So all you're doing is horizontally translating the solutions in a given area. And that's a feature that all autonomous models have. But you can clearly see that the student who knows nothing at the beginning is learning faster. But then the other question, it says, will the student who starts out knowing none of the list ever catch up? So you can see here that it doesn't look like they ever catch up. There's still a gap. Now that gap gets increasingly smaller, but I wouldn't say that they ever catch up, because if you consider, because it's autonomous and they're horizontal translates, whatever this graph goes through, this graph will also have to go through the exact same things. So this one has a head start on it. This one will never catch up because it must go through the exact same arrows that the other one did. What that is going to mean ultimately is no matter how hard you try, you won't catch up to someone that starts ahead of you. Now, is that realistic? Probably not, but this is just a basic model for us to look at. And then on D, I'm going to leave D to you, but let me explain a little bit about what I'm looking for here on D. The idea here is we want to make this model more realistic. So in order to make it more realistic, we have to assume that just because you're learning parts of the list doesn't mean you won't forget parts of the list. So I want you to try to incorporate something into this model. So go back up here, create a new model, maybe call it, something like ODE2, or you can do, you can call it whatever you want, but these are trying to incorporate memory loss, right? So you could do something like this, where you take the model and you subtract M, right? So what would subtracting M from the model do? Well, M is a number here, right? And it has the same units as you have over here. So the units over on the left-hand side of the equation are the derivative units, which are percentage of the list per hour, right? So M is subtracting from that. So you could think of M as sort of the memory loss parameter. So like if M was 0.01, that would say that you lose 1% of the list per hour from your memory. Maybe that makes sense. Maybe that's a decent model to look at. There are other choices as well, right? Like you could model it, the larger the list gets, the more likely you are to forget things. So you could incorporate some type of memory loss here based on the size of the list. That would be called a sort of proportional memory loss model. But I want you to think about in part D, I want you to come up with two ways, and you can use the constant one as well, but come up with at least one other way of modeling memory loss, and then look at the equilibrium solutions. Now, I didn't say much about the equilibrium solution here, but you can clearly see that 1 is the equilibrium solution, because once you get to 1, you've memorized 100% of the list. And without some sort of memory loss in place, once you've memorized 100% of the list, you're just going to stay at that level. But if you introduce some sort of memory loss parameter, then you're not likely to stay at that same level. All right. When you go back to watch this video, you can press pause, rewind, jot down some of these things, but I want you to do your own work here, okay? Don't just copy down exactly what I've done, do your own work, write your own conclusions, and then look at at least 2 of these memory loss models here. You could plot them, talk more about them, things like that. All right, I do want to talk about problem number 2 with you, but in order to do that, I'm going to have to introduce something called Euler's method. And this won't take me very long, but I think it's for the best if we've looked at it before I try to jump in and show you the material there. So this is actually something that I've already uploaded the lecture notes for. We're not going to lecture on this in normal class, but we are going to talk about it here during lab. Because it makes more sense to talk about this during lab. It's a numerical technique. It's perfect for computers. So the question that we're trying to answer with something like Euler's method is, how do we plot solutions to differential equations when we can't actually even solve the differential equation? So we've noticed a couple of times now when we've tried to use the dsolve command on certain equations, Maple just doesn't know what to do. It doesn't know what the answer to the problem is because there really isn't an answer. Like there's not a closed form solution to the problem. This is especially true of nonlinear differential equations. And because of that, no matter how hard we try, we're not going to be able to plot a solution. We're always going to be plotting approximations to the solution. And it turns out for most of the problems in the real world, this is the way that they're solved. You approximate the solutions. And for differential equations in particular, there are many different numerical techniques. Now we're going to talk about the simplest and most intuitive one today, which is Euler's method. But if you go on to take like a numerical methods class, you'll probably dive into some of the others. But this is just a very simple one to get started with. If you're looking for material on this, I would encourage you to read section 2.7 of the text. It's going to give you a good introduction to Euler's method. All right, so what is Euler's method and numerical techniques in general? Well, it's essentially Euler's method that we're going to look at is a technique for solving a first order differential equation. So our equation will look like first derivative of y is some function of x and y, and we have some starting point x naught, y naught. The goal is to take your starting x point, x naught, and extend the solution out to some value x, right? So you could start at 0 and extend it out to 5, right? So you just want to be able to draw the solution from 0 to 5. And all we're going to do is use a certain step size to step off and find a new approximation at each point in that interval. Now there are, in practice, many different methods. We are going to talk about Euler's method today. But I'm also going to try to talk about some of these others along the way, but simply how Maple views things. I do want to talk about something called order. So it turns out that Euler's method is what we call a first order method. RK2, RK stands for Runge-Kutta. It's named after the mathematicians that invented the method. Runge-Kutta 2 is a second order method. You'll sometimes hear this referred to as Hoynes method. So Hoynes method here is another name for what we call an RK2 method. The original Runge-Kutta method is what we call RK4. This is a fourth order method. And RK45, which is actually the method when you do DE plot in Maple, it's using RKF45. And I can show you why that is here in a second when we look at some Maple stuff involving Euler's method. So RKF45 is that method that Maple uses, and it's a fourth, fifth order method. What does order mean? Well, it's actually really kind of simple. Suppose that you have this interval and you want to divide it up into, let's say, 4 subparts. So let's say 4 subdivisions gives you K total error, right? Because remember, these are approximations. So what Euler's method, being a first order method, means is that it's one-to-one with subdivisions and error. So what I mean by that is if we were to double the number of subdivisions, it would have the error. Okay, so Euler would be k/2 total error. That's if you did Euler, because you doubled the number of subdivisions, so that should have the error. Okay, that's what a first order method would do. But if you had Hoyne's method, which is a second order method, what you would actually get there is if you multiplied by 2 here, it would do 2 squared, or 4 total error. It would drop the error by a factor of 4. Right? So doubling the number of subdivisions in a second order method would actually reduce the error by a factor of 4. In a fourth order method, it would be k/2 to the 4th total error, or it would drop it by a factor of 2 to the 4th, or 16. So this is for RK4. And then with RKF45, you get somewhere between a 16th and a 32nd of the error just by doubling the number of subdivisions. Essentially, the order tells you how quickly this thing can converge to the correct answer. How many subdivisions do you need to get good accuracy? So the higher the order of the method, the fewer subdivisions you need to create good accuracy, the fewer points you actually need to approximate along the way. And so we're going to look at approximating this in a little bit. We're not going to do the error stuff in this class. That's best reserved for a numerical methods class. But I did want you to know what is meant by order here. Okay, so what is Euler's method? Well, it's actually really simple. I have the steps involved here, but to be honest, the steps may sound more complicated than they really are. Let me graph this for you and talk about the steps that are involved. So what we're after here is we're trying to plot the solution to some differential equation. So x, y. My differential equation is y prime equal f of x, y. And I'm starting at some point x naught, comma, y naught. So I'm starting this procedure at the only point that we know lies on the solution curve. And that's the initial point. The initial point we know must be on the solution. Now, what we do from there is we say, okay, I know if I plug x naught, y naught into the right-hand side of my differential equation, right? So if I plug x naught, y naught into the right-hand side of the differential equation, that will give me a slope. And the name of that slope is, we're just going to call it A0 for the initial slope. So this point exists in a slope field, and there's an arrow associated with it telling you the direction the solution heads in. So we're just going to say, okay, there's the direction the solution heads in according to the slope field. Let me make that a straight line. Now the question is, how long do I follow that direction? Okay, well, I'm going to break up an interval. So I'm wanting to get all the way out to this point. So I want to approximate what this solution does, whatever it looks like, all the way out to the point x. So I'm going to take the interval between x naught and x, and I'm going to break it up into n pieces. So this is piece 1, piece 2, and so on. And this last piece is really xn, if you want to call it that. Now, I can calculate the distance between each of these. Since there are n of them, it's just the total distance divided by n. We call that the step size. So the step size that my method uses, which we use the letter h for step size, is the difference between x, my end point, and my starting point divided by the number of subdivisions, which is, in this case, n. Sometimes you'll use capital N down here. The method usually calls for capital N, but lowercase n is the same thing. So say, for instance, that my step size was 0.1, right? Then I'm going to follow this initial tangent for 0.1 distance along the x-axis. And then I stop, and I've created my second point on the curve. Now, will that second point actually be on the curve? No, because the arrow here is only accurate at the instant of the initial point. The arrows change, your direction changes over this interval. If the interval is very, very short, like very, very small step size, then there's not too much of a change, which is why this method can be accurate if you have small enough subdivisions. But depending on how big the step size is, we would not expect this point necessarily to be a good representation of the solution if the solution is doing a lot of curving and bending, for example. So all I'm doing here is I want to calculate where this new point exists. Well, this new point, I'll call it y1. How do I calculate y1, this new y value, because I know I'm stopping at x1, the next x value in the interval. How do I calculate y1? Well, it's actually pretty simple. I know the slope, the differential equation, right? The differential equation gives me the slope. The slope at this point is a naught, which is the function value evaluated at x naught, y naught. So if I take the right-hand side of the differential equation, I plug in the initial point, it gives me the slope of this tangent line. That slope is what I'm going to call a naught, which is f of x naught, y naught. Now, I'll just, for the sake of brevity here, write a naught there. What are the other pieces that we know? We know that this distance is h, and we know that this distance is, I'll just call it s for now. So how are those related? Well, you can easily say that a naught is s divided by h, right? Rise over run. Well, the pieces that we know are h and a naught. We know the step size because we know how we spaced apart these subdivisions. And we know the slope because the differential equation provides it. What we don't know is the gain in value here in the y direction. We don't know s, but you can solve for s. S just turns out to be a naught times h. So you can see that here. To get y1, it's just y naught plus h times, and that should say a naught. And this is where a naught is f of x naught, y naught. But in general, you can keep doing that. So I'm going to do the next one, right? So we're at our next point. And the next point is x1, y1. So we plug x1, y1 into the slope. So we plug it into the differential equation to get the slope. We're at a new point, so we're going to get a new slope. That'll generate a new tangent line. So there's the new tangent line that's generated. And I wind up at this point. I need to now say, okay, what is my y2 value at this point? Well, I know the slope is a1. I know that the horizontal distance traveled hasn't changed. It's still h. And I know the vertical distance is h times a1. So I can now calculate y2. Y2 is y1 plus ha1. And now I have y2. And if my goal is to get all the way out to here, you can see how we'll just continue this. I'll get the next slope. And this distance here will be ha2. And we'll just continue on until we get to the end. Now we're going to do an example of this together. The resulting curve that's drawn. So this curve is called the Euler polygon. Okay. So this is Euler's method. We're going to do it in a table. We're going to calculate without the computer to start with. We're going to calculate some approximation to the solution several points away from where we start. And just to show you that, and then I'm going to come back in Maple and show you some more details. So let's look at the following example. We've got a nonlinear differential equation. So I'm gonna go into Maple here in a little bit with you and show you that Maple doesn't really like this differential equation. It's going to have a really hard time solving it, and the solution is going to look terrible. We're going to start at the point 0, 1. So I have a little table here. And this is what you're going to have to be able to do if you're going to do Euler's method by hand, like on a test, for example. You're going to have to be able to fill in a table like this and answer some questions. So our X and Y values for iteration 0, that's just X0, Y0, that's our starting point, right? So our starting point is X0, Y0. So we're starting at X equal to 0, Y equal to 1. That's our starting point, our initialization for the method, if you will. Now we're going to find A0, the slope. Well, the slope, the tangent slope at that point, is simply the right-hand side of the differential equation evaluated at X equal to 0 and Y equal to 1. So this would be 0 minus 1 squared, which is negative 1. Easy enough. I then want to figure out, this is the change in Y. That's what we're calculating here, is the change in Y. So the change in the Y value is the step size, which you've been told for this problem, the step size is 0.1. So the step size times the slope. So we've got a negative 0.1, that's the change in Y. So you take the change in Y and you change the Y value by that amount. So we change the Y value now, subtracting 0.1 from the previous value, we get 0.9. And our step size tells me what the next X value is. So the next X value that we stepped over to was the one we started at, 0, plus the step value is 0.1. So just to remember, this is you're adding H each time, and here you're adding H times A in each time. So you're adding that fourth column each time. So I'll say AK. So H times AK. Okay, let's do another couple of iterations here. So your second slope, A1, would be, let's see, you've got 0.1 for the X. So once again, plugging into the differential equation would be 0.1 minus 0.9 squared, which that value turns out to be negative 0.71. So my H value here is still 0.1, negative 0.71. That'll be negative 0.071. So that's my change in the Y value. If I subtract that here, I'll get 0.829. Okay, and my new X value is 0.2. Okay, let's just do it again. You've got the A2 value, so this is the next tangent slope. Would be 0.2 minus the Y value squared. This turns out to be negative 0.487241. And then if I multiply it by the step size, we're going to get negative 0.04874241. So if I then subtract that from my previous Y value, I get the new Y value, and the new X value is a 0.1 further because of step size. I can then calculate A3. We're almost done. Our goal is to find Y at 0.4. So we're doing 4 steps here. So A3 is the Y value squared there. Turns out to be negative 0.30888681. And so when you step it off, you're going to lose about 0.03. Now, there's something that needs to be mentioned here about like rounding. There are different kinds of errors that can occur when you're doing step-by-step methods like this. You can have what's called rounding error, which is I take something like 0.7802 and I instead round it to 0.7803. You can also have what's called truncation error, which is I just cut off after the 4th decimal point everywhere throughout this, right? So those, once again, those are topics for numerical methods class. We're not going to get into the error here, but understand, like, if this were a problem on a test, I would tell you to carry all calculations out to the 3rd decimal place or something like that, just so that we're all getting the same answers when we write things down. Okay, finally, moment of truth. What is our answer? Well, if I take this last Y change and subtract from the previous Y, I will get 0.7493869. And so the question is, how good a job did we do? Is that a good answer? Okay, so here's where I want to bring in a little bit of Maple to kind of discuss what's going on here. So let me go back over to Maple, and I'm going to just create a new file here because this isn't related. What I'm about to look at isn't necessarily related to what we were looking at before. Let's see if I can get this side by side here. All right, I think that's as good as we're going to do. Okay, so our differential equation here is x minus y squared. So let me go ahead and enter that equation. So y of x equals x minus y squared. So there is my differential equation. All right, so there is a Maple file available to you called an Euler method example, which is basically what I'm going through now. I would recommend that you take a look at it once you're done watching this video. So if I go in and try to desolve this, so if I try to desolve, I'll get, let's see, ODE y of 0 equal 1, y of x, because our initial condition here is y of 0 equal to 1. So if I let Maple just desolve, you can see that it's this horrible looking solution, right? Definitely not something that we want to mess with. So instead, I'm going to have Maple numerically solve this. So you want to pay attention to this because this is a technique that we're going to use a lot throughout the semester. So if I make one simple change to this command, if I take the desolve command, and at the end, I say numeric. Notice it gives me a procedure. So it's running a numerical procedure in the background, and that procedure is RKF45. This is this Runge-Kutta fourth, fifth order method. Now, I want to, and this is what Maple uses in DE-plot, right? It's this method behind the scenes. So I want to actually ask Maple, what is the value of this procedure at 0.4? And I want to compare it to our answer. Now, theirs is an approximation, just like ours is an approximation, but theirs is a much better approximation. So this is as close to the real answer as you would conceivably get. So I want to compare it versus the answer we got just doing a couple of simple Euler iterations by hand. All right, so I'm going to give it a name. All right, so I'm going to call this y solution. So I'm going to call that procedure y solution, and I'm going to ask, what is the procedure when x is 0.5 or 0.4? It tells me that when x is 0.4, it returns a y value of 0.7798. So you can clearly see we're a little bit off, right? We're about 0.03 off after 4 steps. Okay, that's not terrible. Let's plot our Euler method. So if you look at the last slide here, it says draw the Euler polygon. So remember, the Euler polygon is just this thing here. So plot something like this. We could do this by hand and just create a graph and then plot these data points from the table. So just create a data plot of this is 1 coordinate, this is 2, this is 3, this is 4. You see 5 coordinates here. We could plot those 5 coordinates and just draw the line between them. But I'm going to show you how to do that in Maple. So I'm going to show you how to draw the Euler polygon in Maple. So I'm just going to collect the data that we have. I'm just going to call the list data. So lists in Maple are in square brackets. So our first data point is 0, 1. Our second data point is 0.1, 0.9. Our next data point is 0.2, 0.829, then 0.3. I'm just copying what I have in the table there. So that's our data set. I'll just call it data. Okay, that's our Euler data. All right, I'm going to create a couple of plots. I'll call the first plot T1. So I'm going to plot the data set, and I'm going to plot them as points. The symbol that I want to use for the point that's plotted is something called the solid circle symbol. I just want them to show up as nice big circles. And I'm going to increase the size of that circle to size 10. Okay. The second plot that I want to create is using the data. I want to connect the dots, right? So just like we connected the dots on that Euler polygon earlier, I want to plot the data points and I want to have Maple go in and connect the dots. So here I'm going to say style equal line. I'm going to change up my color here just to differentiate it. And I'm going to make the line a little thick. And then the third thing that I want to do is I actually want to plot the actual answer here. So here's Maple's actual answer. Now, I don't want to copy and paste that whole thing because it's going to look terrible. So I'm going to show you a trick here that you really need to learn because it's going to be useful throughout the entire semester. And that is, I'm going to use something called the right-hand side. So if you type in RHS, that stands for right-hand side, and I want to copy down the right-hand side, this right here is what I would copy into here. It goes by the number 1, right? So these labels aren't just for show, they're ways to reference things in the Maple document. So I can say the right-hand side of label 1. Well, the way you do labels is by hitting Command L or Control L. Command L or Control L for label. And the identifier is the label number. So I want to take equation 1, so type of label is equation 1, and I want to use its right-hand side right here. So I just want to plot this. That's what I'm telling it. Plot that. Okay, and I want to plot that from x equal to 0 to 0.4. That's the interval that we're on. And I'm going to choose a similar thickness and a different color here. All right, now that we've got all those together, I want to combine them all onto one plot, right? So remember, the way to combine plots in Maple is to use the plots package. And I want to display T1, T2, and T3 are my 3 plots. And what you can see here is, here's our starting point, 0, 1. And this is our first Euler approximation, our second, our third, and our fourth. And here's how those compare to the actual answers. So this is the Euler polygon in green. This is the actual answer in gold. You can see we're already getting a sizable amount of error. That error would be significantly reduced if we used more points, right? If we used a smaller step size, we would significantly reduce the error, but it would also increase the number of calculations in runtime. So there's a trade-off there. All right, so this is the Euler polygon. This is what would go on this final screen here of the notes. All right, now that we've introduced Euler's method a little bit, I want to go back to your Maple lab and talk about a couple of things that I think you'll find useful for doing problem 2. So on problem number 2, it's looking at the differential equation dy dt equal y. So let me go ahead and write that in. I'll just call it ODE2. I didn't use ODE2 up here, did I? Yeah, I did. I used ODE2 there. So let me hit restart. So the restart command is really nice. If you hit restart, it clears out all the memory of previous things you've entered in that document. So I'm just going to restart because I want to use ODE2 here because it's problem 2. So ODE2. And what I'm going to do is plot the differential equation, or take the differential equation here, which is y of t comma t equal y of t. And we're going to desolve it, which we already know the answer here. This is a pretty simple differential equation. The answer here is just e to the t, right? The derivative of y equal to y, that's from calculus, that's clearly just going to be e to the t. So I'm going to use desolve and plot the analytical solution. So there's the analytical solution. We just said plot right-hand side, Command L, 2.1, equation 2.1. And we're going to do this for some interval here. I'll do 0 to 0.5. So there's the actual solution. There's not much interesting going on there, but we're going to compare it to the actual answer coming up. So this is part A for that problem. There's nothing too difficult for part A. Now in part B, it says create 3 additional plots that use DE-plot to plot an estimated solution for the IVP. Remember, every time you use DE-plot, it's not plotting the actual answer, it's plotting an approximation using one of these numerical techniques. It says use the optional arguments, iterations equal 5 and step size equal 0.1. In other words, I can tell Maple when it uses DE-plot which method to use to do the plot and how big a step size to use and how many iterations to do. So this is why I only made this first plot from 0 to 0.5, because I'm going to tell Maple to use 5 iterations with the step size of 0.1. So I'm going to tell it to graph my solution starting at 0, using 5 iterations of 0.1 size. We're going to go from 0 to 0.5 for these graphs. Now I have this on another Maple line. So for the interest of time, let me copy it over here. But this is what I am wanting you to do, right? I'm wanting you to take the initial plot that we just had together, which is the plot of e to the t, and then DE-plot. We've already learned how to do DE-plot. Here's the new things that have been added. You've got your initial condition, but you also have 5 iterations with step size 0.1, and the method I'm using here is Euler's method. So this is going to create that Euler polygon. Now I'm only interested in the solution here, not the slope field. So notice on all of these, I say arrows equal none because I don't want the slope field showing up. So here I'm calculating Euler's method solution. Here I'm calculating Hoynes' solution. This is the second order one. And here I'm calculating the Runge-Kutta solution, but they're all DE-plot. It's just this optional method, iterations, and step size values that are here, right? That's all I'm doing. Okay. So if I take all those and plot, so I'll need with plots loaded again to make those all show up. So let me make sure I enter each of these. Remember, when you copy and paste things, into Maple, trying to see why it gave me an error here. When you copy and paste things into Maple, it doesn't automatically load them. You have to individually enter each one. Give me this error on all of them. Yeah, so it doesn't like something there. Okay, it seems to make me want to put these here. All right, let me put those in before the initial condition. This worked in my other Maple file, but it was an older file, so maybe they've updated the command here. Okay, so let's see if that works. No, that didn't work. I'll have to think about that and see why that's going wrong. Okay, even if that's not going right, there's something else that we can do to get it that I'm going to show you as well. The other thing I want to show you is a very nice thing in the numerical analysis package. So if you go and load with student numerical analysis. So if you load that package, one of the things that's in that package is something called initial value problem. And so if you load that package, you can do some really interesting things. And this is going to be useful for you computing the error on C and D. Basically, it's going to give you all the information. okay, to complete C and D. So the command is the initial value command. Oh, I think I know what was wrong. Hold on. I think I know what was wrong on the previous thing. Let me copy those back over. I think what was wrong is I called it ODE2 previously. Let's make sure that works. There we go. Okay, there they are. So yeah, I had named it ODE2 here, but on my other file, I'd named it ODE1. So the ODE that we're solving here, that we're plotting, is this really simple one. There's not much difference, but you can sort of see toward the end, right? The green one is the Euler method one, and it's the one that's sort of starting to lag behind, right? Toward, once you get out to 0.5, it's a little bit underestimating the actual answer. But if you compare that with Hoynes' method, which is orange, and RK4, the Runge-Kutta method, which is blue, those are virtually in sync with one another. So this isn't a particularly difficult differential equation for it to numerically approximate. What makes Euler's method bad is if there's a lot of curving. So it depends on the second derivative. So if your second derivative is very large, then Euler's method creates a lot of error, it turns out. But you would study that in a numerical methods class. All right, so the other command that I wanted to show you, and this will help you on part C and D on problem number 2, is if you load the student numerical analysis package, there's something called an initial value problem command. So we're doing initial value problem on ODE2. We're starting at y of 0 equal to 1, and we're going out to 0.5. So we're going from 0 to t equal to 0.5 using 5 iterations or 5 steps. We're going to use Runge-Kutta method, right, which is the sub method there is RK4. We could use RKF45 as well. And here's the really cool thing. I'm going to compare the results from using Runge-Kutta with the results from using Hoyne and Euler. And I'm going to have it output all of this information. If you don't want to refer back to the video, you can just go to the Maple help. So you can just go up here to Maple help, find Maple help, and then from there, find the initial value problem command, and it'll tell you everything you need to know about it. And if I hit enter, notice it gives me a pretty nice, I'll make this bigger. It gives me a pretty nice table to look at here. So it's telling me what step of the iteration I'm on, what is Maple's actual best guess at the answer, what does the Runge-Kutta fourth order method give, then what is the error from the actual answer to Runge-Kutta, what does Hoynes' method give, and what is the error there, what does Euler's method give, and what is the error there. And the nice thing is this initial value problem gives another output mode other than table mode. So other than information, you can also say output a plot. So if you say output plot, then it shows you, this is basically the same thing as this, okay? It shows you Euler's method, Runge-Kutta, and Hoyne all right there, along with the highest quality numeric solution that Maple has, which for all intents and purposes would be the most accurate actual solution. So this will help you to answer the questions on parts C and D of problem 2. All right, I think that's a pretty good introduction to what I'm asking you to do on numbers 1 and 2. There's not another Euler's method problem in this. So this isn't, these particular commands aren't something that you really need to memorize. Just, I want you to have seen it before. What you do need to be able to do with Euler's method is fill in a table like we did with the notes earlier. So the table involving where we went in the table together and did it step by step from the lecture notes that you have online. I do need you to be able to do something like that. But this is the information that we would have talked about together Monday night in lab, and I just wanted to get it out in front of you so that you can kind of start working on your lab. As far as I'm concerned, after this, you have problems 1 and 2 done. After Wednesday's class, you can do problems 3 and 4 and 5. You can already do problem 6. There's not much there. And then after Friday's class, you can do 7 and 8. And then it'll be due the following Monday, September 20th. If you have questions, please ask. Okay. I don't want you to sit there for an hour at a time and just stare at your screen and not know what to do. Okay. I want you to ask questions and I'll help you as best I can get started with the Maple stuff and get to where you feel pretty confident about your ability to do some of these Maple problems. All right. Y'all have a good day.